22 is not the correct time.
Welcome to yet another seminar on IMEX time-stepping schemes. This is focusing on Runge-Kutta time-stepping and how to do HEVI. I'm going to tell Dale Duran how to do HEVI and in comparison to semi-implicit. So motivation. All models of the atmosphere and ocean combine implicit and explicit time-stepping. But it's only quite recently that we've started looking in more detail of the theory at how they should be combined. When I started this work, the Met Office, that's point one, no, point two, the Met Office were concerned about HEVI, horizontally explicit, vertically implicit, and this would introduce splitting errors, and they were concerned about the loss of accuracy with doing horizontally explicit, vertically implicit. So I'm going to look at that. So requirements for a time-stepping scheme, second order overall, and second over, not just second order implicit and second order explicit, but the interactions between implicit and explicit second order. Third order explicit part, so that the advection, the truncation or the truncation of the advection can be diffusive rather than dispersive. We would like to damp high frequencies without losing order of accuracy. So there's no computational modes. I'm not. It's clearly not that important. It's not a good enough motivation itself for using a Runge-Kutta scheme. But this is the requirements that I'm working on here.
These people are coming next week, right?
Yeah. Yeah.
You gotta have a go.
Well, I mean, should wait till they're here.
Yeah, I'm not going to argue no computational modes. Everything's got computational modes. No loss of accuracy in HEVI mode with implicit gravity waves. So that's something we saw this morning in Dale's talk, that when he used implicit gravity waves in HEVI mode, the accuracy was lower than implicit with an explicit gravity waves. Unconditionally stable for vertically propagating waves, so astable, and conditionally stable for horizontally propagating waves, so stable with a short for a particular time step. Todd.
I hesitate, but I must. The whole reason to use implicit is because there's something that you want to step over. If the thing that you're trying to model is important, it should be explicitly time stepped. And so am I wrong there?
What's the motivation for implicit time stepping if you don't want to take a look, if you're not willing to degrade your accuracy at all of that process?
Well, there's clearly you're going to have a degrading in the accuracy. So you want all the gravity waves to be implicit. Some of them slowly you're going to resolve, but there are some fast ones that you can't resolve. And so so you want your implicit scheme to be sufficiently accurate, not so as not to damp out all your gravity waves, but allowing some of them to propagate much more quickly.
Okay, but there's no parsing of. I mean that's a far more nuanced statement than the no loss of accuracy in HEVI mode of. Right. What you're saying is you don't want to damp out the things you care about, but this is.
Well, this is not. So when I say no loss of accuracy, that is for a test case. That is not for the. That is not based on analysis of the scheme. So the test case doesn't. You don't have to get accurate acoustic waves to get good results from the test case. So this is accuracy with respect to a numerical experiments. Sure.
Well, I would have to. Without the implicit is not. It's not because it's implicit that it's not accurate.
Because it's a long time step.
With the same time step, it's much more accurate than explicit.
Yes, yes, yeah. But it's because you're taking you might have a CFL of 100 for an acoustic wave. So I'm going to look more at the way in which the compressible Boussinesq equations can be split in between the terms can be split between implicit and explicit. We've got in advective form the momentum equation, a continuity equation in advective form, and a buoyancy equation. And so the semi-implicit with explicit gravity waves, you'll have the gradient of pressure implicit and the divergence implicit. And so then the momentum equation is substituted into the pressure equation to get a Helmholtz equation, and that's semi-implicit with explicit gravity waves. But we need implicit gravity waves because the gravity waves are very fast. So then to get the difference between, to get the implicit gravity waves, the vertical velocity, I've got u dot g hat, so that is in fact w, also needs to be implicit. So then you substitute this w into here, and then into the momentum equation, then momentum equation into the continuity equation, and then you get semi-implicit with implicit gravity waves.
Sorry, so B is your density?
B is buoyancy, so it's density, yeah. Horizontally explicit, vertically implicit. I'm now redefining what is fast and what is slow. So now I'm assuming just the vertically propagating waves are fast and the horizontal propagating waves are slow with respect to the grid. So now I've split up the horizontal velocity momentum and the vertical momentum, and this is the standard way that you will see horizontally explicit, vertically implicit. So you've got just the vertical pressure gradients, and the vertical buoyancy is fast, and the horizontal component of the divergence. So that's the vertical component of the divergence. The vertical, these are the terms involved in the vertical propagation of acoustic waves. So I'm calling this. This is the way that a few papers recently, I think Duran and Blossy and Ulrich and Jablonowski have done HEVI splitting. And I'm calling this UFPREF, which means U forward, pressure forward. So in the U equation, it's forward in time, and the horizontal pressure part is forward in time. I'm proposing UFPREB, which is U forward, pressure backward. So now I've split up the equations in a different way, and I've still got the horizontal pressure gradient explicit and the vertical pressure gradient implicit, but now I've got the whole of the divergence as a fast term, whole of the divergence implicit in their pressure equation. And so this is nothing new. This is forward backwards for horizontal acoustic waves. However, it is different to the way other people have used an IMEX scheme for HEVI. So now my horizontal acoustic waves, which are controlled by dp by dx and du by dx, one part is explicit and one part is implicit. However, by saying this is implicit, it's not really implicit, because u is already calculated. I calculate this equation first, all explicitly. So I'm just using the most up-to-date value of u, so it's the obvious thing to do.
And some of us have been doing it for 40 years.
Oh yes, yeah, it's forward backwards.
But this isn't what we actually did in the Blossy-Duran reference.
You say it's not?
No.
The Blossy and Duran and Ulrich and Jablonowski, and when people apply an IMEX HEVI scheme to horizontal acoustic waves, they do UFPREF.
But we did all of the sound. We did the whole 2D solve.
So you're semi-implicit?
Semi-implicit in all the acoustic
There's no
waves.
HEVI.
For all the acoustic
Oh, okay.
waves.
Oh gosh, that was an oversight. Okay, Ulrich and Jablonowski did HEVI like that. And yeah, so this is how UFPREB is, how split explicit has always been done, and Messinger 1977 said forward backwards, this is how to do horizontal acoustic waves. But that was with just a straight Euler forward, Euler backward step. And I'm saying we can use the same thing by doing pressure U forward, pressure backward, and apply that with any Runge-Kutta IMEX scheme. And so I'm going to be looking at the differences between UFPREF and UFPREB. So we've already seen the definition of a Runge-Kutta IMEX scheme for double butcher tableaus. So I'm solving an ODE with a slow part and a fast part, and then you have different coefficients for the explicit part for the slow part and the implicit terms for the fast part, with all these coefficients which Frank showed as well. So the explicit tableau has got all zeros down the diagonal and zeros here, and the implicit, these are all zeros, but there are now coefficients, non-zero coefficients on the diagonal. Some important properties of Runge-Kutta IMEX schemes. Stiffly accurate is accurate in the stiff limit for if you, for example, if it's completely incompressible. There are two different. Asher et al. Said in order for a scheme to be stiffly accurate, you want this last row to be the same as that last row, and this last row to be the same as that last row, which is really a big constraint on the scheme. There's a lot fewer schemes you can use that have got those two rows the same and those two rows the same. What that gives you is that your final stage is implicit, which is kind of what you want. You think if it's nearly divergence free, you want your final stage to be implicit. However, Pareschi and Rosso said that what you want is to be asymptotically accurate. So that's in the stiff limit, you want to be controlled by the accuracy of your explicit scheme, and that's got a lot. The constraints, that's a lot easier to meet. You just want, for that, you want the determinant of A. This is the A matrix to be non-zero. So there are a lot more schemes like that. So I want to know: is asymptotically accurate? Is that actually enough for to get good solutions for incompressible flow? There are other things that's properties of the schemes that appear to be useful in some situations. It can be useful to have if you have all these C's the same as all these C's. This is your sub-step sizes. Then that means that you don't have. If it means you're taking the same sub-step for implicit and explicit. So that should reduce the splitting errors. But then there's also, you can have all these W's the same as these W's. So then when you've taken all your sub-time steps, are you going to add them up the same? And if you add them up the same, that can also reduce splitting errors. But if you do them, but you can't do it all exactly the same, because otherwise they wouldn't be different. And then you want strong stability preserving, so you want it to damp the high frequencies.
But that limits, though, your choices.
Oh yeah, yes.
Quite a bit.
Yeah, I don't think you can't have all of these. But these are some of the things that I'm looking at, thinking which do I want. So there's a naming convention for the schemes. I've got a name, and then K, the first number, is the order of the explicit scheme, which the order of the explicit scheme is we're concerned with because we want for example, the advection or the slow waves to be accurate. Number of implicit stages, so that is going to dictate how expensive it is. Number of explicit stages, and the overall accuracy of how the two implicit and explicit combined.
We've had strong stability preserving come up several times here. And these schemes are designed to be this as was mentioned, this convex sum of forward differences, which if you have an appropriate physical differencing to go along with, they give you a certain type of stability, but they don't in general imply anything about more general types of stability. I'm surprised that you have them as damping high frequencies necessarily, for example. They can be quite unstable, in fact, for some types of spatial formulations.
Well, it'll depends on the spatial discretization.
Right,
so,
right.
yes,
In other words,
yeah.
it doesn't mean much until you have the right spatial
Yes,
discretization.
yeah.
But I agree,
Yeah.
it has to go in conjunction with the spatial
Yes.
discretization being
Yeah.
TAD or some property like that.
Yeah.
Excuse me, Hilary, when you mentioned the implicit part being expensive, you're just talking about one-dimensional implicit?
Yes, well, I'm going to compare semi-implicit globally with just vertically implicit.
But this is a specification for IMEX schemes. So in the IMEX scheme, it's less obvious that the cost is determined by the implicit solve, right?
No, yeah. So a load of butcher tableau, which I'm not going to talk about in great detail, but some of them are, so that is stiffly accurate in that tableau, but not in that one. This one, so this is a third order overall, so that looks great. And all of these numbers, those numbers are the same as those, so that looks as if it's got no splitting error. So this one looks really, really good. Crank-Nicholson with an outer iteration to update the explicit terms, and then another of these schemes from Pareschi and Russo. This one has got. This one is not stiffly accurate. These two lines, that line is completely different from that one, and that one is different from that one. And then there's a new Runge-Kutta scheme from Ulrich and Jablonowski, which I've rewritten as a butcher tableau so I can compare it. And this one has actually only got, if you look at all those zeros there, it's only got one implicit stage. So that may have advantages. This work I've done with Sarah Jane on the stability analysis of these. First of all, following Duran and Blossy, we analysed the stability on a generic wave equation like this with a slow part and a fast part. So here the slow part is horizontal and the fast part is vertical. And we show that almost all of them are unstable. However, I still implemented them and they were really stable. So the reason for that is that you're not necessarily modelling, if you're actually solving, say, the acoustic wave equations or gravity wave equations, you're not actually solving an equation exactly like this. You may put it like this, but then when I'm talking about UFPREB, you might say that, well, these horizontal waves, they should go partly in there and partly in there. So the stability analysis on this fast-slow wave equation doesn't necessarily help you with a particular wave equation, the way you split up the terms between implicit and explicit.
Yes, and FR functions, or is it a simple constant? How do you take this?
S and F, they're constants.
Constants.
Real constants. For the sake of the analysis.
Okay.
But then they'd have spatial discretization terms when you're actually solving a real PDE. So instead, we've been analysing the acoustic wave equations. And then, so you can rewrite the acoustic wave equations for U, W, and P as expression more like this, where S, F, and G are matrices. And so now you can calculate you can put this into the von Neumann stability analysis and calculate your amplification factors, but now the amplification factors are 3 by 3 complex matrices. And so you can look at the largest magnitude eigenvalue and the smallest magnitude eigenvalue. And the largest magnitude eigenvalue will tell you the stability, and the smallest one will tell you the maximum damping that you could get. So for 3 of the schemes, this is the stability analysis for this Crank-Nicholson with deferred correction. If I analyse just the generic wave equation, not the acoustic wave equation, and so the red is greater than 1, so it's unstable, and this is the horizontal acoustic current number and the vertical acoustic current number. So this is unstable along the x-axis, so it's unstable for all time steps for the horizontally propagating wave. So just no, can't use that. However, if you analyse it, so this is the analysis for UFPREF and this is UFPREB. There are 2 plots for each. This is the smallest magnitude eigenvalue and this is the largest magnitude. So again, for UFPREF, it's this black line shows 1.1 plus epsilon. For UFPREF, it is still unstable for all time steps along the explicit limit. So that really is saying the same as this. But UFPREB, it's now stable. So the analysis of the generic wave equation isn't actually telling us about the stability of solving the compressible Boussinesq equations. And then this is the Crank-Nicholson with 4 iterations. This is a scheme that has been, with 4 outer iterations, been used by the Met Office successfully. And then Sarah Jane analysed it and found that it's unstable along the x-axis it's stable, but just off the x-axis it's unstable. But it's working. So how come? Well, the answer is if you actually use it to solve particular wave equations, which are not solved in the same way, UF-pref is stable and UF-preb is also stable. And then finally, in order to, if you have got a wave equation that is behaving more like the generic wave equation, such as maybe including Coriolis or advection, if you replace one of your implicit steps with an explicit step, so instead of having a half or a 1 there, I've moved it all to there. Well, actually, this is Tom Allen from the Met Office gave us this suggestion. It's now stable for the generic wave equation and stable in other configurations as well. So it can be fixed, but I don't know if it's necessary to fix it. And now some of these more exotic Runge-Kutta IMEX schemes. This one with 3 implicit stages and 3 explicit stages appears to be unstable for the generic wave equation and UF-pref, but stable for UF-preb. SSP 3332, so it's second order, third order explicit and 3 stages of each. It's got this region of instability for the generic wave equation, which we don't know how important that is. However, it goes away in UF-preb and UF-pref mode. And then a higher order scheme, again with a strange region of instability, which goes away, UF-preb and UF-pref and UF-preb. It looks as if you just look at the explicit limit, this scheme looks as if it has a very long current number, maximum current number. However, it's got that spike that comes in there. Actually, it's not nearly as long as the explicit limit. So the implicit explicit mix is making it a lot less stable.
So it's making so it's stiffness leakage.
Stiffness leakage.
Yeah, it's when your implicit solver affects the explicit stability region. Is that what's happening there?
Yes. Yeah. More schemes. So again, we've got 2 more schemes where analysing the generic wave equation, we've got these nasty regions poking down into the origin, making it appear unstable, but they go away in UF-pref mode. This one, however, is a lot worse in UF-preb mode. This one is one of the ones that is stiffly accurate. These 2 lines, bottom 2 lines are the same. However, unstable in UF-preb mode. Strang carryover scheme of Ulrich and Jablonowski is it's very symmetric because it uses Strang splitting. So when you do linear analysis and analyze linear waves, the implicit and explicit solutions don't interfere with each other. So you've got the explicit stability in this direction and the implicit stability in this direction. It looks lovely. And it's also fine UF-pref and UF-preb. So I've been, the test case I've been using is the vertical slice that Duran and Blossy used. We've got a gravity wave generator here. This is the buoyancy and the winds. And this is the horizontal velocity. Gravity waves generated by these stream function doing this. And wind is going this way, and so the gravity waves are generated upstream. And I've got errors for a load of different time steps. So these lines are semi-implicit, and these lines over here are HEVI. And of the HEVI ones, the dashed lines are UF-pref, and the dashed dotted lines are UF-preb, and they all have got implicit gravity waves. So what we'd really like to see is, for example, the semi-implicit coming down here and the continuing on down here, so it's not losing accuracy in HEVI mode. However, so a lot of the schemes, for example, this SSP scheme, there's a jump. It's a lot less accurate in heavy mode. And then, so what some of them do, for example, these black and blue ones up here, that red scheme, which is one of the Crank-Nicholson schemes, trapezoidal schemes. It's coming down here, second order accurate, and it continues on down there. However, it's only accurate in UF-PREV mode. In UF-PREF, it's way up here. So what I think is, for HEVI with implicit gravity waves, you are treating dp by d, you've got different temporal discretization for dp by dx and b, and this is also du by dx. However, if it's heavy, these two are always going to be different, but if you give du by dx, if you solve du by dx with the same time-stepping scheme as the buoyancy, then your gravity waves are a lot more accurate. Because these much less accurate schemes only occur when using implicit gravity waves. So I've also looked at much coarser resolution. So that was the hydrostatic test, near hydrostatic test case. I've made it even more hydrostatic by making the resolution even coarser. And I've been looking at these. A lot of the schemes don't use a final implicit stage, which seems dangerous. And so I've been looking at the impact of that. This is the divergence, of velocity divergence at the end of a time step for one of these schemes, which is not stiffly accurate, which looks like a disaster in comparison to what the divergence should look like. And if you use trapezoidal, which has got a final implicit stage, it all looks fine. So should we discount all these schemes which don't have an implicit final stage? Well, so in the Butcher tableau, there's the final implicit stage, and then there's another stage after that. If you take the velocity from after the final implicit stage rather than after the final stage, it's absolutely fine. So if we were thinking about using one of these schemes, and say if you're going to advect moisture, to advect the moisture and for all the other parameterizations that need a nearly divergence-free velocity field, it might be an idea to use the velocity from after the final implicit stage rather than the final velocity, and sort of redefine where the end of your time step is. That's conjecture, really. So this is work I've done with Nigel Wood at the Mess Office and Sarah Jane, but these are my conclusions, not condoned by them. Heavy models should use UF-PREV splitting rather than UF-PREF. The most accurate and stable schemes are not stiffly accurate. And a solution might be to use a velocity from after the final implicit stage for affecting other quantities. The Strang carryover scheme, I didn't go through all the schemes on that graph, but it was, for having only one implicit stage, it's reasonably accurate. The linear stability analysis is not telling us everything we need of the acoustic mode is not telling us everything. For example, one of the schemes that I originally mentioned, this Asher Ruth's Spiretti scheme, the analysis, in the analysis it looks similar to all the other schemes, but it's completely unstable in every configuration. I don't know why that is. The SSP schemes of Pareschi and Russo are looking very promising, in particular this one is third order explicit accurate 3-stage scheme. So further work, I'd like to look at triple quadruple Butcher tableau, because there are more terms in the equations. For example, should the advection have yet another time-stepping scheme, and tracer advection and nonlinear advection, split explicit could be defined as another Butcher tableau. The compressible Boussinesq equations, the implicit part is linear. So to solve the Euler equations, then the fast terms are nonlinear, so they need to be linearized. which is going to have implications for the relative accuracy of different schemes. So that is a caveat on this work as well. Thank you.
Quick question for you. So on the Strang carryover method, that's the Paul Ulrich's, you said it has one implicit solve. What's the order of that method?
It's second order.
It's second.
Because the implicit terms have two do have two solutions, like Crank-Nicholson, but the first one is done explicitly, reusing the solution from the previous time step. That's, well, done explicitly is my interpretation of it. Their interpretation is it reuses the final implicit solution from the last time step.
Can you put it back up, sorry?
Yeah, but you use about how many stages? I thought there was like 4 stages or more.
Well, they do one explicit.
Oh, yeah.
Yeah.
One explicit stage. There's a lot of zeros in here which don't need to be calculated.
Sure.
So one explicit stage for the fast terms, and then you've got a third order Runge-Kutta scheme explicit, and then a final implicit solve. So it's a really big butcher tableau. It's inefficient showing it as a butcher tableau, but it's actually
But you
not
actually have a whole column of zeros there.
at the top.
No, the penultimate column.
Yeah, that's because there's no implicit in the explicit butcher
That's the
tableau.
explicit part.
No, in
Oh.
both the explicit and the implicit. So this is
There
your
are
variable,
zeros.
it's just not used for anything. That's
I think that's. I don't know why that is. I can't remember.
But anyway, so it has 3 explicit stages and then 1 implicit solve, correct?
Yes, and one extra explicit stage in the implicit
Fine,
tableau.
okay.
Yeah.
But it's only second order.
Second order overall, third order explicit, which is probably what we want, but it doesn't, because it's Crank-Nicholson and the implicit tableau. It doesn't damp high frequency modes, so that would be a possible reservation. It's
I was just trying to physically think about this result. I think it's your second one again, about how you want the bottom line of the butcher tableau to match the next one up, to keep everything nice at the end time. Is it slightly, so as you step through the Runge-Kutta, you are getting intermediate time values, and if you were stepping through these intermediate times, doing, say, all the acoustic modes to have everything balanced at each individual time, would you then be able to take an arbitrary linear combination of these results and be okay? And so I'm wondering if there's a slightly different way to think about this physically, mathematically, and generally than just trying to match the bottom 2 lines.
yes. If you chose the right linear combination of them, then you would get, it could be stiffly accurate, which is why I'm not sure about that actually, because so none of the schemes, all of the schemes which have, so for example, these schemes which have the bottom 2 rows differently, they when you look at the divergence at the end of the time step, it does look messy. It's not just a linear combination of the nice divergences that have come before.
Well, I didn't think I explained it very well, so I was surprised you were agreeing with me actually. But it seems to me as you go through the implicit and explicit iterations, you may or may not wind up with having done a complete set of non-divergence calculations at the same intermediate time level. But if you did happen to do that, if you happen to pick a tableau where you went to each intermediate calculation, you did your explicit part of divergence and pressure gradient, and you also did the implicit part in the vertical, then you might be able to take an arbitrary linear combination and slot something that's non-divergent. But if you have sort of gone to different spots and sort of done your explicit stuff over a different time interval, or, well, this was part of this. Part of that was part of...
Or an even more general case of that is, assume you have a intermediate point at which you have the right divergence properties. Then you're allowed to take, presumably, an arbitrary linear combination of those weights and the final ones.
Yes.
The final ones all the way.
Right.
Which is why some of these schemes have the weights where you add them all up. these numbers, 6/6, 2/3, are the same as these ones. So they're trying to do that. They're trying to take a linear combination of all the substages. However, no, you can't have all these, that row the same as that row, and that row the same as that row. So if you take a linear combination of what's gone before, they're different substage values. And so some of then other schemes have these values, the substeps the same, but then when they take a linear combination of what's gone before, they're taking different amounts from each.
But that's not typical, right? So the nice thing about this, I keep harping on the Kennedy and Carpenter, I'm giving them a lot of press, the Kennedy and Carpenter IMEX ARK methods is that they have these properties that, let's see, right, so at every stage, right, you can essentially interpolate, right, between stages, you still get the same order of accuracy. And that's what they call dense output. Meaning that they have all those properties are built into the method, so they're designed that way. So I think what you're saying, if I understand correctly, is if you, for example, wanted your velocity to be divergence free at some intermediate stage, you would have it at any part of that stage. If you were to sample at any part between the two stage values, you still would have the same thing. But they're designed specifically to be that way. I'm not sure that that's what I was saying, that some of these SSP methods, I'm not sure you can do that if there's other constraints to build them.
Yeah. I should probably not take the stage anymore and make it into a more...
Well, no, at least I think we
general
started a discussion already.
Discussion, there you go.
But I don't need to answer everybody's
That's true.
points.
Yeah.
But it's fun.
How do you think about conservation in this system? Because I noticed in your set of basic equations, you've got potential temperature, pressure, but not a prognostic continuity equation. So you basically get the mass through the gas law as a diagnostic, and so typically you won't be conserving. Are you looking to solve in flux form, or are you really going to do vective form, or?
It took quite a lot of persuading for Nigel Wood to get me to solve with vective form equations, which I was quite reluctant to do. Because it's such a simple Cartesian grid, it is actually equivalent to flux form, and so mass and energy are conserved. But I'd much rather do it in flux form equations, and much easier to get it all conserved for different grids.
Well, but if you take the finite difference form of your pressure equation and your theta equation and use those to work back through the gas law to get a continuity equation, it's going to be pretty hard to rigorously conserve.
Joe, what do you worry about conserving what? Mass?
Yeah, conserving mass. That you've got. I mean, you've got a continuity equation. Your rho dt is del dot rho v, and that's if you satisfy that, then you've got exact mass conservation. And in these advective form systems where we're typically solving often pressure and theta prognostically, and then density just comes out as a residual. And then anytime you screw around, like for example, there have been some folks that have used reduced sound speed in the pressure equation as a nice way to be able to take a larger time step and not affect the results very much. But what it does affect is that basically puts a source or a sink term into the continuity equation. If you just work backwards to see what the effective continuity equation is in that system, you see all of a sudden there's a source term that popped up in that equation, and so that's why it's for enforcing conservation, solving a continuity equation prognostically has a nice some nice features to it, and
Oh, so you're saying the problem with solving the continuity equation implicitly is that it's going to be harder to conserve? Is that what you're saying?
No, if you're solving a prognostic continuity equation, then you enforce conservation of mass. Okay.
Yeah.
There is no
No.
prognostic continuity equation. And so if you take those equations and work backwards to see what your numerical continuity equation is, based on the finite difference form that you use for the pressure and the buoyancy equation, depending on how you do your numerics in those two equations, you'll see some
Yeah.
things that
Yeah.
look like little
Yeah.
source or sink terms in the continuity.
Well, one of the things I'd like to do, I'm not suggesting that these are the right equations to be solving. They're the equations I've solved for these test cases. I don't think that the IMEX schemes will work well for flux form Euler equations as well. Which,
But are you thinking that at least the stability properties of the schemes applied to this set will carry over to the flux?
the thing that
That's-
may not carry over is that as soon as if you have flux form Euler equations, the fast terms are now nonlinear. So you've got to linearize and update the nonlinear bits. And so you may want to take, for each implicit solve, you may want to have an update. So it may then change the balance of which IMEX scheme is best, because if you're you could just put the nonlinear parts into the explicit tableau, or you might want to keep them with the same substages, so you might want to update them after the time step. So it might mean that you actually want to stick to something like Craig-Nicholson, because all your explicit parts and the deferred corrections are actually look the same.
But you could also do non-linear implicit. No, I mean, I'm a bit, I'm coming from a different angle, but people who have looked a lot at this and at the consistency of the mass and momentum equations, people with compressible flow in aerodynamics implicitly.
Yes, with Newton solver. Yeah.
But that's
Yeah,
for a high Mach number, right? For low Mach number, there's a completely different story. We've never been able to beat an IMEX method with a fully implicit method, not for low Mach number flow. I agree with you, the high Mach flow.
Yes. But, they are, I also get, you get non-linearity is not